February 27th, 2026. In a control room filled with quiet screens and soft humming machines, something extraordinary was confirmed. Earth had just detected a signal. Not from a nearby satellite. Not from a passing asteroid. Not even from within our own galaxy. This signal had traveled for 12 billion years. 12 billion years. To put that into perspective, when this signal began its journey, the sun did not exist. The Earth did not exist. The Milky Way was still young and chaotic. Life as we know it was unimaginable. And yet, something out there sent a message, and we just received it. It wasn't a message in the way we usually imagine. No pattern, no code, no alien transmission. It was radiation, powerful radiation, radio waves, and X-rays arriving together. That detail matters, because in the universe, those two signals don't usually come as a pair. Not like this. Astronomers had been studying a distant patch of sky, a region so far away that even the most powerful telescopes struggle to see it clearly. The light from that region is ancient. When we observe objects that distant, we are not looking across space. We are looking back in time. That's how astronomy works. Light travels at a finite speed, about 186,000 miles per second, fast enough to circle the Earth 7 times in 1 second. But even at that speed, crossing billions of light years takes billions of years. So when detectors on Earth picked up these radio waves and X-rays, they weren't witnessing something happening now. They were witnessing something that happened when the universe was only about 15% of its current age. Imagine receiving a postcard mailed before human civilization began, except this postcard was sent before our planet even formed. That is what happened. At first, it looked like many other distant cosmic sources, a faint glow, a spike in radiation, data points on a screen. But as researchers analyzed the signal, something unusual emerged. The energy output was enormous, far too enormous for a typical star. This wasn't stellar radiation, it wasn't a supernova, it wasn't a gamma-ray burst fading away. The spectrum told a different story. It pointed to something far more extreme, a quasar. Now, if you've never heard of a quasar, here's what you need to know. A quasar is not a star, it's not a galaxy. It's what happens when a supermassive black hole at the center of a galaxy is actively feeding. Black holes themselves are invisible. They don't emit light. But when matter falls toward a black hole, it doesn't drop in quietly. It spirals, it accelerates, it heats up. And as it heats up, it glows, sometimes brighter than the entire galaxy around it. That glowing region is called an accretion disk. And when it shines intensely across vast cosmic distances, we call it a quasar. Quasars are among the brightest objects in the universe. They can outshine trillions of stars. And this signal, the one Earth just detected, had the unmistakable signature of 1. But something was different, very different. Most quasars tend to be categorized by how they emit energy. Some are strong in radio waves, and others are strong in X-rays. The mechanisms behind those emissions involve powerful jets, magnetic fields, and extreme physics. But rarely do we see both signals, intense radio emission and intense X-ray radiation, blasting out simultaneously at this scale. That combination is unusual, suspiciously unusual. As scientists dug deeper into the data, they traced the source to an object cataloged as ID 830, a name that sounds simple, almost forgettable. But what it represents is anything but ordinary. ID 830 sits so far away that its light has been traveling for roughly 12 billion years, which means we are seeing it as it was in the distant past, at a time when galaxies were smaller, when the cosmos was denser, when the first generations of stars were still shaping the structure of everything we see today. The early universe was not calm, it was violent, chaotic, rapidly evolving. But even in that era, there were expectations, rules, limits. Based on everything we know about physics, black holes take time to grow. They start small, often from the collapse of massive stars, and gradually accumulate matter over millions or billions of years. Growth is not instant. It is regulated, constrained. There is even a theoretical ceiling on how fast a black hole can consume matter. But we'll get to that. For now, let's focus on this. ID 830 was already enormous when the universe was still young. And that should not be possible. When researchers calculated its properties, the numbers forced them to double-check their models, then triple-check. The brightness implied a black hole of staggering mass, hundreds of millions of times the mass of our Sun, in an era where such size should have been extremely rare, possibly impossible. Let's pause and think about scale. As at the center of our own galaxy lies Sagittarius, a star, a supermassive black hole about 4 million times the mass of the Sun. It sounds big, it is big, but compared to what was detected in this ancient signal, it's small. ID 830 appears to be nearly 100 times more massive, and it existed billions of years earlier in cosmic history. That timeline doesn't add up, not easily. But before scientists could even confront the problem of mass, they had to answer a more basic question. What exactly are we looking at? Was this truly a quasar, or something else entirely? They analyzed ultraviolet light, they examined X-ray spectra, they compared the radio intensity to known models. Every indicator pointed to the same conclusion. This was a feeding black hole, an active one, devouring matter at extraordinary speed, so extraordinary, in fact, in that it might be breaking one of the fundamental growth limits we believe governs black holes. And that is where this story becomes even more unsettling. Think about what it means to detect something from 12 billion years ago. This signal began its journey long before our solar system formed. It traveled through expanding space, through shifting cosmic structures, past forming galaxies, through regions of gas and dust, uninterrupted, unscattered. Yet for billions upon billions of years, until in 2026, it brushed against our detectors and revealed the existence of something ancient and monstrous. We often imagine the universe as quiet and distant, but moments like this remind us it is still speaking. We just need to know how to listen. The early universe was a place of extremes. Temperatures were higher, gas clouds were thicker, stars were more massive than many we see today. Some of the first stars may have been hundreds of times the mass of our Sun, short-lived, explosive, seeding the cosmos with heavier elements. It was an era of formation, of rapid transformation, and somewhere in that chaos, a black hole began to grow, faster than expected, larger than expected, brighter than expected, and powerful enough that its radiation is still reaching us across time. Oh, but here's the question that now hangs over the astronomical community. If ID 830 existed that early, how many others were there? Was this an anomaly, a rare cosmic accident, or is our understanding of early black hole growth incomplete? Because if one object can reach such mass so quickly, perhaps the early universe was far more efficient at building monsters than we thought. And that possibility changes everything. It affects how galaxies formed. And how structure developed, how matter organized itself on cosmic scales. One object, one signal, but enormous implications. For now, scientists are cautious. Extraordinary claims require extraordinary evidence. But the data is compelling. Radio waves, X-rays, 12 billion years old, all pointing back to a single ancient source. D 830. A quasar from the dawn of cosmic history, a black hole that appears to have grown too large, too fast. Shown in the next part of the story, we'll dive deeper into what makes this object truly shocking. Because the mass is only the beginning, there is a physical limit that black holes are not supposed to exceed, a cosmic speed limit, and the evidence suggests that ID 830 may have shattered it 13 times over. And if that is true, then the early universe was not just violent, it was extreme beyond our current imagination. The signal has arrived, the data is real, and the mystery has only just begun. When astronomers say they are looking at something 12 billion years away, they don't just mean distance, they mean time. Every photon collected from ID 830 left its source long before our planet existed. Those photons began their journey when the universe was still in its adolescence, turbulent, crowded, and evolving at a breathtaking pace. We are not observing a current event, we are witnessing a fossil, a preserved moment from deep cosmic history. And like any fossil, it tells a story about a world that no longer exists. To understand what that world looked like, imagine rewinding the cosmic clock. 12 billion years ago, galaxies were smaller and more irregular. Collisions were common. Vast clouds of hydrogen and helium were still collapsing to form the first generations of stars. The universe was only about 15% of its current age. Structure was still assembling itself, gravity was busy, and somewhere inside one of those early galaxies, a black hole was feeding, violently. The object we now call ID 830 was first identified as a quasar candidate because of its brightness. Even across unimaginable distance, it shone with extraordinary intensity. That brightness is not trivial. When something that far away appears bright, it must be intrinsically powerful, unbelievably powerful. Think of a candle seen from across a room. It looks small but visible. Now imagine seeing that same candle from across an ocean. If you can still see it, it's no candle. It's a lighthouse, or something far more intense. ID 830 is not a candle. It is a lighthouse blazing across billions of light years. But brightness alone doesn't define a quasar. Astronomers look at spectra, the fingerprints of light. By splitting incoming radiation into its component wavelengths, scientists can determine temperature, composition, motion, and energy output. ID 830's spectrum revealed something unmistakable: hot gas spiraling at enormous speeds, extreme ultraviolet emission, intense X-ray radiation, and powerful radio signals, all signatures of a supermassive black hole actively consuming matter. This was not a quiet object. This was a feeding engine. Now here's where the tension builds. And the quasars are powered by accretion, the process of matter falling into a black hole. But matter doesn't plunge straight in. It forms a rotating disk. Friction heats that disk to millions of degrees. The hotter it gets, the more it radiates. That radiation is what we detect. In the case of ID 830, the luminosity was staggering. When researchers calculated the implied energy output, they had to ask, how massive must the central black hole be to generate this kind of power? Yet the answer shocked them. Approximately 440 million times the mass of our Sun. 440 million. Let that sink in. For comparison, at the center of our own galaxy lies Sagittarius, a star, weighing about 4 million solar masses. Impressive. But ID 830 appears to be nearly 100 times more massive, and it existed billions of years earlier in cosmic history. That timeline creates a problem. Because black holes don't simply appear at that size. They grow, slowly, over vast spans of time. They begin as smaller seed black holes, perhaps a few tens or hundreds of solar masses formed from collapsing stars. Then they accumulate matter, gradually, regulated by physics. But ID 830 seems to have skipped steps. It was already enormous when the universe was still young. And that raises a fundamental question: how? To understand why this is difficult to explain, consider the age of the universe at that time. If the universe today is about 13.8 billion years old, then 12 billion years ago places ID 830 less than 2 billion years after the Big Bang. In cosmic terms, that is early, very early. Building a 440 million solar mass black hole in under 2 billion years is not trivial. It requires sustained growth at near maximum theoretical efficiency. And even then, models struggle. Which is why some astronomers describe objects like ID 830 as overmassive for their epoch. They are too big, too soon. Now imagine you are part of the research team. You run the calculations once, then again. You test alternative models. You check for measurement error. Could gravitational lensing be amplifying the brightness? Could there be multiple sources blending together? But the data remains consistent. ID 830 is singular, and it is massive. And this is where the story shifts from surprising to unsettling. Because size alone isn't the only anomaly. When scientists measured the X-ray luminosity, they found something even more extreme. The black hole wasn't just large, it was feeding at a furious rate. So furious, in fact, that it may have exceeded what we call the Eddington limit, the theoretical maximum rate at which a black hole can grow without blowing its own fuel supply away. That concept is critical, and we'll explore it in depth next. But here's the key idea. If ID 830 was already 440 million solar masses, and still growing aggressively, then its growth history must have been extraordinary, perhaps even chaotic. But before we jump ahead, let's return to the signal itself. Radio waves and X-rays. Why is that combination important? Because radio emission often signals the presence of powerful jets, narrow beams of particles launched at near light speed from the region around a black hole. X-rays, on the other hand, come from extremely hot gas near the accretion disk. Producing both at high intensity requires a delicate balance of conditions: magnetic fields, angular momentum, matter supply. It is not common to see both channels blazing so strongly at the same time. And yet ID 830 appears to do exactly that, which means whatever was happening around this black hole 12 billion years ago was not ordinary. It was extreme. Think about the environment. The early universe was denser, galaxies were closer together, gas clouds were more abundant. Collisions between galaxies could funnel enormous amounts of matter towards central black holes. Perhaps ID 830 sat at the center of a young galaxy undergoing violent mergers. And perhaps tidal forces ripped gas inward in torrents. Perhaps it devoured entire stars that wandered too close. We don't yet know the exact mechanism, but we do know this: something fed it, relentlessly. As the team compared ID 830 to other known early quasars, patterns emerged. There are other massive black holes in the early universe, but each one challenges our understanding in slightly different ways. ID 830 stands out not only for its mass, but for the apparent rate at which it was accumulating matter. That combination, large and still rapidly growing, is rare. It suggests a phase of accelerated growth, a feeding frenzy, and possibly a temporary violation of the limits we thought were strict. The discovery has broader implications. Black holes are not isolated curiosities. They influence their host galaxies. Their radiation and jets can heat surrounding gas, suppress star formation, and shape galactic evolution. If black holes like ID 830 were common in the early universe, then galaxy formation itself may have unfolded differently than we assume. The early cosmos may have been dominated by rapidly growing central engines capable of altering entire galactic ecosystems, and that changes our narrative of cosmic history. But perhaps the most humbling aspect of this discovery is perspective. For 12 billion years, this signal traveled unnoticed. Yes, it crossed expanding space as the universe stretched around it. It moved through regions that would one day host galaxies like ours. It passed by stars that had not yet been born. And finally, after a journey longer than most structures in the universe have existed, it reached us, a small planet orbiting an ordinary star, with instruments sensitive enough to decode its story. There is something profoundly poetic about that. Yet poetry aside, the physics demands explanation. How did ID 830 grow so fast? Was it born from an unusually massive seed black hole? Did it experience sustained periods of near maximum accretion? Or did it undergo brief but extreme bursts of growth that temporarily exceeded theoretical limits? That last possibility is especially intriguing, because if confirmed, it would mean that black holes in the early universe could, under certain conditions, break the rules, or at least bend them dramatically. In the next segment, we confront that possibility directly. We examine the Eddington limit, the cosmic speed limit of black hole growth, and we explore the evidence suggesting that ID 830 may have exceeded it by a factor of 13. If that is true, then this ancient monster did not simply grow. It accelerated beyond what physics comfortably allows, and that would force us to rethink how the first giants of the universe came to be. If the signal has told us where to look, the mass has told us something is wrong, now we must examine the limit that may have been broken, because the true shock of ID 830 is not just how big it was, it's how fast it was eating. To understand why ID 830 is so disturbing to astronomers, we need to talk about a limit, a boundary written into the laws of physics, a speed limit for black holes. It's called the Eddington limit. Yet, and according to everything we know, black holes are not supposed to exceed it. The idea is surprisingly simple. When matter falls toward a black hole, it doesn't disappear instantly. It forms a swirling disk, an accretion disk, spinning faster and faster as gravity pulls it inward. As that matter compresses and heats up, it emits radiation, light, X-rays, energy. And here's the crucial part. Radiation pushes back. Light carries momentum. When enough radiation is emitted outward, it creates pressure, radiation pressure, that opposes gravity. So if a black hole tries to consume matter too quickly, the radiation it produces pushes incoming gas away. It's like trying to eat while blowing air outward at full force. At some point, the outward pressure balances the inward pull of gravity. That balance defines the Eddington limit. It is the maximum stable growth rate. Imagine gravity pulling matter inward with enormous force. Now imagine radiation pushing outward just as powerfully. At the Eddington limit, those two forces are equal. Go beyond that limit, and theoretically, the radiation should blast away the fuel supply. Accretion slows down, growth stabilizes, the system self-regulates. That's the theory, and for decades, it has worked beautifully. Our models of black hole growth are built on it. So when researchers analyzed the X-ray brightness of ID 830, they were not expecting what they found. The luminosity suggested that this black hole was accreting matter at roughly 13 times the Eddington limit. 13, not slightly above, not marginally exceeding. 13 times beyond what stable physics predicts. If accurate, this is not just fast growth, this is runaway growth. Let's be clear, black holes can briefly fluctuate. Yeah, they can experience bursts. But sustained accretion at 13 times the theoretical limit? That pushes into extreme territory, because at that level of radiation output, the surrounding gas should be violently expelled. The black hole should choke on its own brightness. Yet the signal from 12 billion years ago tells a different story. ID 830 was not choking, it was feasting. Now, before we imagine physics collapsing entirely, we need nuance. The Eddington limit assumes a certain symmetry. It assumes radiation is emitted roughly evenly in all directions. But what if the radiation isn't isotropic? What if geometry plays a role? In some theoretical models, matter can flow inward through dense, optically thick channels, while radiation escapes along different paths, like steam escaping through vents while water continues to pour into a drain. In that scenario, super-Eddington accretion becomes possible. Not stable forever, but possible. And perhaps that's what we are witnessing here. But even that explanation raises deeper questions. If ID 830 was accreting at 13 times the Eddington rate, how long did it sustain that pace? Surely not for millions of years. That would produce a black hole of unimaginable scale. Instead, researchers estimate something astonishing. This extreme feeding phase may have lasted only about 300 years. 300 years. In human history, that's the time between Shakespeare and the American Revolution. In cosmic time, it's less than a blink. Think about the journey of the signal. We are observing a moment that lasted only 3 centuries in the life of the universe. 3 centuries out of nearly 14 billion years. The odds of catching such a brief, violent phase are small. And yet, we did. Now that suggests either extraordinary luck, or that such phases were more common in the early universe than we assumed. Now consider what might trigger such an event. Black holes don't spontaneously decide to overeat. They need fuel. A sudden influx of fuel. Perhaps a massive cloud of gas collapsed inward. Perhaps a galactic merger funneled material toward the center. Or perhaps, and this is one of the more dramatic hypotheses, a massive primordial star wandered too close. Early stars may have been far larger than those we see today. Hundreds of solar masses. Short-lived, unstable. If one of those giants strayed into the gravitational reach of ID 830, it would be torn apart, stretched, shredded, its material spiraling inward in a torrent. That could trigger a super-Eddington episode, a feeding frenzy, and a brief violation of equilibrium. And here's where things become philosophically unsettling. We tend to think of physical limits as rigid, but in extreme environments, especially in the early universe, limits can become thresholds rather than walls. Under certain conditions, systems can exceed them temporarily, like an engine redlining for a short burst before overheating. ID 830 may have been redlining, pushing its environment to extremes, converting infalling matter into radiation at breathtaking efficiency, and in doing so, accelerating its own growth beyond expectations. But remember, this isn't speculation without evidence. The X-ray luminosity measured from ID 830 is what drives this conclusion. X-rays originate very close to the event horizon, near the hottest, most energetic regions of the accretion disk. The intensity of those X-rays acts like a thermometer for black hole feeding rates. And that thermometer is reading off the charts. Combine that with the radio emission, likely indicating powerful jets, and you have a picture of a system operating at extraordinary energy levels. Not quiet, not stable, but explosive in its efficiency. If this super-Eddington phase lasted around 300 years, it may have contributed significantly to the black hole's mass. Short bursts of extreme growth can, over time, build giants quickly. Think of compound interest. If small gains over long periods build steadily, but sudden windfalls accelerate everything. If early black holes experienced multiple such windfalls, their rapid emergence becomes easier to explain, and that reshapes our understanding of cosmic evolution. But here's the uncomfortable possibility. What if our baseline assumptions are wrong? What if the early universe allowed sustained super-Eddington accretion more frequently than we thought? What if dense gas environments, while high merger rates and primitive galactic structures created conditions where black holes routinely exceeded theoretical limits? In that case, ID 830 is not a rebel, it's a clue, a window into a more extreme cosmic youth. Science advances through anomalies, through data points that don't fit comfortably. ID 830 is one of those data points. It forces astronomers to revisit simulations, to tweak parameters, to explore new regimes of physics under early universe conditions. Yet, because if black holes could grow faster than we assumed, then the timeline of structure formation shifts. Galaxies may have matured earlier. Massive systems may have assembled more rapidly. The cosmic dawn may have been brighter and more violent than our textbooks suggest. And yet, we must remain cautious. Extraordinary luminosity can sometimes be amplified by orientation. If jets are pointed toward us, brightness appears enhanced. If gravitational lensing magnifies the signal, mass estimates could be skewed. Scientists account for these possibilities. They test alternatives. They refine measurements. But as of now, the evidence still points to something remarkable. ID 830 was feeding at extreme rates, possibly 13 times the theoretical limit, in a universe that was still young. Pause and consider the scale of that statement. A black hole, hundreds of millions of solar masses, in the early universe, consuming matter at a rate that challenges fundamental theory, and we know this because a handful of photons survived 12 billion years of travel, arriving precisely when our species has developed the instruments to interpret them. There is something awe-inspiring about that timing. In the next segment, we dive deeper into what might have triggered this super-Eddington phase. Was it a collapsing gas reservoir, a violent galactic merger, or the destruction of an enormous primordial star? Because whatever fed ID 830, it did so with extraordinary intensity. And for a brief moment in cosmic history, this black hole became one of the most extreme objects the universe had ever produced. The speed limit was supposed to hold. But in the distant past, something pressed the accelerator. If ID 830 truly exceeded the cosmic speed limit, then something extraordinary must have fed it. And black holes do not grow in isolation. They require fuel, gas, dust, stars. And in the early universe, fuel was abundant. But abundance alone does not explain intensity. To trigger a super-Eddington burst, a feeding episode 13 times beyond the theoretical limit, something dramatic must have occurred. Something sudden. Something catastrophic. Let's return to the early universe. 12 billion years ago. But galaxies were not the majestic spirals we admire today. They were compact, irregular, turbulent systems. Gas clouds collided frequently. Star formation rates were higher. Massive stars lived fast and died violently. Some of the first generations of stars, what astronomers call population 3 stars, may have been enormous. Not 10 times the mass of the Sun, not 50, possibly hundreds. These primordial giants formed from nearly pure hydrogen and helium. Without heavy elements to cool the gas efficiently, star-forming clouds could collapse into far more massive objects than we typically see today. They burned hot, they burned bright, and they burned briefly. Now imagine one of those giants orbiting near the center of a young galaxy. At the center sits a growing black hole, perhaps not yet 440 million solar masses, but already substantial. Gravity dominates the region. Orbits are unstable. Perturbations from nearby stars or gas clouds alter trajectories. And then, the star drifts too close. When a star approaches a black hole within a certain distance, known as the tidal radius, gravity no longer pulls evenly. The side of the star closer to the black hole feels a stronger force than the far side. The difference stretches the star, elongates it, distorts it. And if the tidal forces exceed the star's own gravity, the star is torn apart. This is called a tidal disruption event, and it is one of the most violent spectacles in the universe. The star does not disappear instantly. Instead, it is pulled into a long stream of stellar debris. Some of that material escapes, but much of it spirals inward, forming a temporary accretion disk, a dense, chaotic torrent of matter. Imagine pouring an ocean into a drain all at once. The inflow would be overwhelming. For a black hole, here that sudden surge can ignite an intense burst of radiation, potentially pushing the system into super-Eddington territory. If ID 830 devoured such a giant, the The consequences would be dramatic. The accretion disk would brighten, X-ray output would spike, jets could intensify, radio emission would strengthen, and for a short time, perhaps a few hundred years, the black hole would grow at an extraordinary rate. And this aligns eerily well with the estimated 300-year super-Eddington phase inferred from observations. 3 centuries of cosmic gluttony, then stabilization. But was it truly a star? There are other possibilities. Galactic mergers were far more common in the early universe. 2 young galaxies colliding could funnel enormous amounts of gas toward their central black holes. When gravitational forces compress gas inward, the central regions can become flooded with fuel. In that scenario, ID 830 may not have consumed a single star. It may have feasted on entire clouds. Vast reservoirs of interstellar matter collapsing inward. Either way, the key factor is sudden inflow, a rapid supply of matter capable of overwhelming normal equilibrium. Now consider the scale of energy involved. When matter falls into a black hole, not all of it crosses the event horizon. A significant fraction of its mass is converted into energy through extreme heating and radiation. Einstein's equation, E=mc², reminds us that even a small amount of mass can produce staggering energy. If a massive primordial star, say 200 times the mass of our Sun, were partially consumed, the energy output would dwarf most stellar events. For hundreds of years, the region would blaze. Jets could extend across thousands of light years, and radiation would flood surrounding space, and from 12 billion years away, we would eventually detect it, which is exactly what happened. There is another layer to this. In the early universe, metallicity, the abundance of heavy elements, was low. That affects how gas behaves. Lower metallicity gas cools differently. It can remain hotter and more dynamic. This may allow accretion disks to become thicker, denser, and more chaotic. Some models suggest that under such conditions, radiation can become trapped within inflowing material. Instead of escaping outward and halting accretion, photons are dragged inward with the gas. This phenomenon, sometimes called photon trapping, can enable sustained super-Eddington accretion. If that mechanism operated around ID 830, it could explain how the black hole temporarily bypassed the usual limit. The early universe may have provided a unique laboratory for extreme growth. But what makes this scenario compelling is not just theoretical plausibility, it's timing. The estimated 300-year duration is consistent with a tidal disruption event or a major gas inflow episode. Not millions of years, not billions. A brief, violent phase. A spike. Caught in the act. We are not seeing the entire life of ID 830, we are seeing a flash, a moment of excess. A frozen in cosmic history. Think about the improbability of that. If the feeding frenzy lasted only 300 years and the universe has existed for nearly 14 billion, then the fraction of time represented by that burst is minuscule, yet our detectors captured it, which raises an intriguing possibility. Perhaps such bursts were not rare in the early universe. And perhaps black holes frequently underwent these growth spurts during periods of high merger activity and dense gas supply. If so, then supermassive black holes could assemble far more rapidly than standard models predict. The early cosmos may have been an era of accelerated construction. There is something almost mythic about the image of a black hole devouring a giant star, a cosmic predator consuming a titan. But this is not fantasy. Tidal disruption events are observed in the nearby universe today. We have seen stars being shredded by black holes. We have recorded their flares. Scaled up to the early universe, with more massive stars and denser environments, the spectacle would be even more intense. ID 830 may represent one of those scaled-up extremes, a predator in a young cosmos. And yet, we must balance imagination with evidence. We do not have a photograph of the event. As we have radiation signatures, spectra, energy distributions, from those clues we reconstruct possibilities. Astrophysics is, in many ways, cosmic forensics. We examine the light, we infer the crime. In this case, the crime may have been the destruction of something enormous, but regardless of the exact trigger, star or gas cloud, the implication remains profound. ID 830 did not grow quietly. It experienced an episode of extreme accretion. As an event powerful enough to leave a detectable imprint across 12 billion years of expanding space. That is extraordinary, because most objects in the early universe are too faint for such detailed study. Yet this one was luminous enough to announce itself, to demand attention, to challenge theory. And now we arrive at a deeper question. If ID 830 underwent such a feeding frenzy, what did that do to its host galaxy? Black hole growth is not a private affair. And the energy released can heat surrounding gas, it can suppress star formation, it can regulate galactic evolution. This feedback process shapes the structure of galaxies over cosmic time. If early black holes frequently entered super-Eddington phases, their feedback may have been far more dramatic than we assumed. The architecture of the early universe could have been sculpted by these violent bursts. In the next segment, we step back from the feeding event itself and examine an even stranger detail: the paradox of simultaneous radio and X-ray emission. Because even if ID 830 devoured a giant star, even if it exceeded the Eddington limit, the dual radiation signature remains unusual. It suggests a complex interplay of jets, magnetic fields, and disk geometry, and it may hold the key to understanding how this ancient monster operated. The giant may have fallen, the disk may have ignited, and the black hole may have grown. But the signal we detect carries more than just evidence of hunger. It carries clues about structure, about physics under extreme conditions, about a universe still in its formative years. 12 billion years ago, in a young and restless cosmos, something immense was torn apart. Its matter spiraled into darkness. Its energy radiated outward, and today that radiation whispers across space, reminding us that even in the earliest chapters of cosmic history, there were monsters. By now, the picture seems dramatic enough. An ancient black hole, 440 million solar masses, growing at 13 times the theoretical limit, possibly triggered by the destruction of a primordial giant. That alone would make ID 830 remarkable. But there is one more detail, a detail that makes astronomers pause. Because even if everything we've discussed is true, there is still something about this object that doesn't quite fit. It's the combination of signals, radio waves, and X-rays, blazing at the same time. To understand why this matters, we need to step into the structure of a quasar. At the center sits the black hole. Around it, the accretion disk, glowing, rotating, superheated. Above and below that disk, magnetic fields twist and coil. Yet under the right conditions, those magnetic fields can launch jets, narrow beams of particles traveling at nearly the speed of light. Those jets are responsible for powerful radio emission. Meanwhile, X-rays are typically produced very close to the black hole, in the inner accretion disk or in a region called the corona, where particles reach extreme temperatures. Now here's the tension. In many models, strong jet production and strong X-ray emission don't peak simultaneously. And there's often a trade-off. When jets dominate, the inner disk structure can change. When X-ray output is extreme, jet formation can weaken. The system shifts between states: balance, reconfiguration, energy redistribution. But ID 830 appears to be doing both. At full intensity, it's like finding an engine that is simultaneously operating at maximum combustion and launching twin exhaust flames kilometers long, both systems demanding enormous energy. Both operating at peak output. That is unusual, not impossible, but rare, especially at this scale. The radio emission suggests powerful relativistic jets. Jets require magnetic field alignment, rotational energy, and disk structure that supports collimation, the focusing of particles into narrow beams. Meanwhile, the X-ray brightness implies a blazing inner disk, hot, dense, and radiating intensely near the event horizon. So how can both coexist? One possibility lies in geometry. If the accretion disk is thick, as expected in super-Eddington regimes, radiation may not escape evenly in all directions. Instead, it can be funneled, concentrated, beamed. In that case, both X-rays and radio emission could appear amplified depending on our viewing angle. We might be looking almost directly into the jet, or along a privileged line of sight. Orientation matters in astronomy. But orientation alone may not fully explain the strength observed. Another possibility involves the early universe environment. Remember, 12 billion years ago, galaxies were denser. Gas supply was abundant. Magnetic fields were evolving. Conditions were more chaotic. In such an environment, black holes might not behave like the ones we observe in the nearby universe. They may cycle through states more rapidly. They may sustain extreme configurations longer. Or they may operate under slightly different physical balances due to metallicity and density differences. In other words, ID 830 may not be breaking physics. It may be revealing a regime of physics that we rarely observe today. There is also the concept of magnetically arrested disks. In certain models, magnetic fields can accumulate near the black hole to such an extent that they partially regulate the inflow of matter. Under these conditions, energy extraction becomes extremely efficient. Jets can become exceptionally powerful. At the same time, dense inflow can continue to produce strong X-rays. It's a delicate interplay. Gravity pulling inward, magnetic pressure resisting, radiation escaping, particles accelerating. The region near a supermassive black hole is not simple. It is a battlefield of forces, and ID830 appears to be winning on all fronts. High accretion rate, powerful radiation, strong radio jets in the early universe. The combination suggests an object operating near the extreme boundary of what black hole engines can do, not quietly evolving, but roaring. This dual emission also matters because it helps confirm the interpretation. Radio emission alone might suggest a jet-dominated system. X-ray emission alone might indicate hot inner accretion. But together, they strengthen the case that we are observing a fully active, dynamically complex quasar, one in a highly energetic phase, possibly in transition, possibly in overdrive. There is something profound about that image. A black hole, already enormous, not simply resting at the center of its galaxy, but actively shaping it. Jets blasting outward, possibly influencing star formation across thousands of light years, radiation heating surrounding gas, energy redistributing matter on galactic scales. And all of this happening when the universe was still young, when galaxies themselves were just learning how to assemble. This is why the paradox matters, because it suggests that early supermassive black holes were not merely passive endpoints of gravitational collapse. They were dynamic architects. They may have played a far more aggressive role in shaping cosmic structure than we once believed. As if ID830 is representative, even partially, then early galaxy evolution models need refinement. Perhaps feedback mechanisms were stronger. Perhaps black hole growth and galaxy growth were more tightly linked from the very beginning. But here's the part that keeps scientists cautious. The universe is vast, and our sample size is still small. Each early quasar we detect adds a piece to the puzzle. Some are radio quiet, some are X-ray bright, some appear overmassive. And ID830 combines multiple extremes in one object, which makes it invaluable, but also dangerous to overgeneralize from. Science must move carefully, even when discoveries are exciting. Still, the pattern is emerging. Over the past 2 decades, astronomers have found more and more massive black holes in the early universe, each one stretching the limits of growth timelines, each one nudging models toward faster formation scenarios. ID830 may be the latest, and perhaps one of the most striking examples because it doesn't just challenge mass expectations, it challenges growth dynamics and emission behavior simultaneously. And remember, we are seeing this object as it was. We don't know what became of it. Over billions of years, it may have continued growing. Its host galaxy may have merged with others. Its jets may have shut down. Its radiation may have stabilized. Today, 12 billion years later, that region of space is unrecognizable compared to what we observe in this snapshot. But this snapshot is enough. Enough to question, enough to reconsider, enough to inspire new simulations and deeper observations. The radio and X-ray paradox is not just a curiosity, it is a diagnostic, a fingerprint of extreme physics, a signature of a black hole engine running at extraordinary capacity. And it reinforces a larger theme. The early universe was not quiet. It was energetic, efficient, relentless, perhaps even more extreme than we imagined. In the final segment of this story, we step back. We ask the broader question. What does ID830 mean for our understanding of cosmic history? Was this object a rare accident, a statistical outlier, or a representative of a hidden population of early monsters? Because if many black holes grew this fast, then the architecture of the universe may have been built more quickly than we thought. And the cosmic dawn may have been brighter, hotter, and more violent than any simulation has yet captured. The signal reached Earth. We decoded its message. And what it tells us is unsettling. The universe, in its youth, may have been a place of runaway growth, of engines pushed beyond equilibrium, of giants born too soon. One ancient black hole, one signal, but implications that stretch across cosmic time. We began with a signal, radio waves, X-rays, 12 billion years old, a whisper from a time before Earth existed. Now we end with a question. What does it mean? ID830. 830 is not just a distant quasar. It is not just another data point in a catalog. It is a challenge to our timeline, a challenge to our models, and a challenge to the comfortable assumption that the early universe was simple. Because if a black hole could reach 440 million solar masses when the universe was less than 2 billion years old, then something about our understanding is incomplete. Let's step back and see the full picture. A young universe, dense, chaotic, rapidly forming stars and galaxies. At the center of one such galaxy, a black hole grows, faster than expected, and larger than expected. Then for roughly 300 years, a blink in cosmic time, it erupts into a feeding frenzy, accreting matter at 13 times the Eddington limit, blazing in X-rays, launching powerful radio jets, shining so intensely that its light survives 12 billion years of cosmic expansion. And finally, that light reaches us, a civilization that has existed for only a fraction of that time, with instruments precise enough to detect it. There is something humbling about that. For most of cosmic history, Earth was not there to witness anything. Dinosaurs did not see the signal pass by, neither did early mammals, nor early humans. The radiation from ID 830 traveled silently through space while continents shifted, species evolved, and civilizations rose and fell. And only now, in this narrow window of technological capability, have we become aware of it. Yes, it makes you wonder how many other signals are still traveling, how many ancient stories are still on their way. But humility does not erase the tension, because the existence of ID 830 forces us to rethink growth in the early universe. Supermassive black holes were not supposed to become giants so quickly. The standard model assumes seed black holes form from collapsing stars, then grow gradually through steady accretion and occasional mergers. But steady growth has limits, time constraints, Eddington constraints, efficiency constraints, and yet here we are, facing an object that seems to have accelerated beyond them. So we ask, was ID 830 an anomaly, a rare alignment of conditions, a statistical outlier that doesn't rewrite the rulebook, or is it a glimpse into a hidden pattern? And because if early black holes frequently underwent super-Eddington phases, if dense primordial environments allowed rapid growth spurts, if tidal disruptions and mergers were common enough to fuel repeated bursts, then supermassive black holes may have assembled far earlier than we assumed. And if they did, then galaxy formation timelines shift. Feedback processes intensify. The entire architecture of the early universe becomes more dynamic, more aggressive, even more extreme. In that scenario, black holes are not passive endpoints of gravitational collapse. They are engines, central regulators, cosmic accelerators. They shape the galaxies that surround them. They determine how gas cools, how stars form, how structure evolves. If ID 830 represents a broader population, then the early universe was not merely forming galaxies, it was being sculpted by rapidly growing central monsters. There is also a deeper philosophical layer. For decades, we have believed that the laws of physics impose firm boundaries. The Eddington limit is one such boundary, a mathematical equilibrium between gravity and radiation. But nature often finds ways to operate near the edge, not breaking laws outright, but exploring their extreme regimes, under unusual conditions, in rare environments. ID 830 may not be violating physics. It may be revealing physics under pressure. As physics stretched to its limits in a young cosmos, science progresses this way, not by confirming what we expect, but by confronting what surprises us. Each unexpected observation forces refinement, simulation adjustments, new hypotheses, deeper questions. ID 830 is not the end of a story. It is the beginning of a new chapter in understanding early black hole growth. And yet, we must resist sensationalism. This is not proof that physics is broken. And it is not evidence of exotic unknown forces. It is a puzzle, a demanding one. But puzzles are what drive astronomy forward. Already researchers are refining models, examining how super-Eddington accretion behaves in low metallicity environments, simulating gas inflow under early universe conditions, testing how magnetic fields interact with thick accretion disks. Each new model attempts to reconcile the data, to explain how a black hole could grow so large and so fast. But even as theory advances, the image remains striking. Somewhere in the distant past, in a galaxy we will never visit. A black hole devoured matter with extraordinary intensity. Jets pierced intergalactic space. Radiation flooded its surroundings. And for 300 years, it burned brighter than almost anything else in the universe. Then, the frenzy subsided. The system stabilized, and the light continued its journey across expanding space, through cosmic time, until it brushed against Earth. It is easy to feel small in that perspective, but there is another way to see it. We are the universe becoming aware of itself. The photons that left ID 830 12 billion years ago carried information. They encoded mass, energy, velocity, structure. For billions of years, that information traveled unobserved. Now it has been decoded, interpreted, understood, at least partially. That is not small. Well, that is extraordinary. Still, the question remains, how many other early monsters exist beyond our current detection limits? Are there black holes even more massive, even earlier in cosmic history? Are we only seeing the brightest examples, the tip of an iceberg hidden in the dark? Future observatories may reveal more quasars, more extreme growth cases, more challenges. Each discovery adding depth to our understanding of the first billion years after the Big Bang. Because that era matters. It is the foundation upon which everything else rests. The distribution of matter, the formation of large-scale structure, the emergence of galaxies like the Milky Way. Understanding how quickly black holes grew during that epoch tells us how quickly order emerged from chaos, how rapidly the universe transitioned from simplicity to complexity. NID 830 is one piece of that transformation, a dramatic one, but still a piece. So we return to where we began, a signal, detected on Earth in 2026, radio waves, X-rays, from 12 billion years ago. It is easy to think of astronomy as passive observation, as simply watching distant lights, but moments like this remind us that we are participants in a dialogue. The universe emits. We listen. And sometimes, what we hear reshapes our understanding. ID 830 may not be the last object to challenge black hole physics. It may not even be the most extreme, but it stands as a reminder that the early universe was not gentle. It was a place of accelerated growth, of intense radiation, of giants emerging quickly, perhaps too quickly. And somewhere in that chaos, a monster was born. Not in darkness alone, but in light bright enough to reach us across 12 billion years. The signal has arrived. And the models are evolving, the questions are multiplying, and the universe, vast, ancient, and still unfolding, continues to surprise us.